Okay, hello everyone. Welcome to the talk. So I'm Bing Li, assistant professor from UT Dallas. Also, there's two collaborators. One is Yixun, another is Professor Du from University of Minnesota, Twin Cities. So today I'm going to talk about an encoding scheme to enlarge practical DNA storage capacity by reducing primer-payload collisions. So for this talk, it's a little bit different from the previous DNA storage talk, which focus on the end-to-end system design. For this one, we mainly focus on one specific issues of DNA storage. Okay, so here are the outlines of today's talk. So first of all, I want to introduce the introductions, why we want to use the DNA storage, and also the motivations of that. And then I may cover some background of what is a DNA storage and what's kind of the issues in the DNA storage. For example, what is the primer-primer collisions, primer-payload collisions. After that, I will briefly introduce our proposed scheme, so-called collision-aware code algorithms, and then we will show the experimental result, and finally we will conclude our finding or observations. So currently we are living in the big data era, right? So there's a huge amount of emerging technologies coming out, including autonomous driving, edge devices, social media, and so on and so forth. So all those emerging technologies are generating a huge amount of data. And in the big data eras, the International Data Corporation predict by 2025, the total amount of data in the world will reach 175 zettabytes. And 4 years ago, 2020, the total amount of data is 44 zettabytes. So for these 5 years, the total amount of data in the world increased 4 times, right? So basically, the data is double almost every year. And in the future, there's a huge demand for the storage system to store all those amount of data. So to store those data, so basically, this is kind of traditional storage devices we have, right? So hard disk drive, non-volatile memory, tape, and so on and so forth. However, so if we just try to categorize all those data, so this is the pyramid of storage devices from the top to bottom. We have the CPU, register, cache memory, SRAM, right? Main memory, solid state drive, magnetic disk, and so on and so forth. So based on this figure here, from the top to bottom, so basically those devices increase the capacity and the lifetime. And from bottom to top, it's increase the speed and also the cost. Okay. So, but for those devices, there's two types of challenges of existing archive storage. The first one is the supply of storage is not keeping pace with the increasing demand. So if we look at this figure here, in 2019 here, there's about 0.6 zettabyte storage supply. And at that time, probably we just need such kind of amount of storage devices, right, to store those data. But when we reach into about 2020 to 2030, the storage supply expand about 19% per year, but storage demand expand 50% per year. So you can see the huge difference between the storage demand and also the storage supplies. So by 2030, there's about 20 zettabyte storage efficiency. So we want to fill this gap, and people try to find emerging storage mediums like glass or DNA and so on and so forth. Right? And this is the second challenge of the existing archive storage. So the existing storage medium cannot preserve data long enough. Right? So we have the video streaming, smart cities, healthcare, scientific discovery data. We want to store in the really long-term persistent storage mediums. However, for the typical or the traditional storage medium like magnetic tape, hard disk drive, or even solid state drive, so the tape up to 50 years, maybe some people mention 20 to 30 years. The hard disk drive around 3 to 5 years with the guarantees or warranties of the vendor, right? So, but it may last 10 years at most. And solid state drive is about 5 to 10 years. It totally depends on how much write you have, right, for those storage devices. So, but obviously it's not long enough for us to store all those videos, pictures, and so on and so forth. And also data to has to be migrated from obsolete devices to new devices every few years because we don't want to lose data we store in those devices, right? And then it will introduce huge maintenance. For DN storage, so basically DN storage has two big advantages. One is DN storage has really long persistency or durabilities. And secondly, DN storage has really high or extremely high area densities. So if we look at the x-axis here is indicate the lifetime of those storage devices. So disk about 3 to 5 years, flash 5 years, tape is 5 to 30 years, DN storage may last like 1,000 years. And the y-axis here indicates the area densities here. So the DN storage may reach to like maybe 1 million gigabits millimeters cube, right? So it's kind of much larger, a much higher area densities compared to the traditional storage mediums. So then this is a potentials of DN storage, but we do want to explore the practical DN storage capacity, the challenge and the solutions. I will indicate in the future slides. Okay, so here is the background of the DN storage. So first question might be what is the DN storage, right? So there's 4 basic nucleotides of bases in DNA, A, T, G, C. A, T are associated with each other, C, G are bonded with each other. And for this kind of DN storage, we use this like double helix structures, right, to form a stable DN strings. And for DN storage, we have the read and write operations. For write operation, first of all, we have binary data, and then we need to have encoding data to convert or encode data from binary domain to the ATGC sequences. So here is one simple example. You can encode, for example, data 00 to A, 01 to T, 10 to CG, and 11 to C, right? After you obtain the sequence, ATGC sequence, you want to assembling some metadata information, for example, ECC error correction code or internal index, and also the primers. So this is kind of used for the random access. Later, I will introduce that. And then you have a synthesizer, or you want to synthesize all those ATGC sequences into the molecular form. Normally, we have the DN string length about 150 to 300 bases. Of course, based on the biotechnology developing, this length can be enlarged maybe to 1,000, 2,000, and so on and so forth. Okay, so this is the basic process of the write operations in the DN storage. On the other hand, for the read operations, so first of all, we have the sequencing machine or sequencers like nanopore or the next generation sequencers to sequence all those molecular form data into the binary digital domain. We got ATGC sequences, and then we try to extract the payload information. Probably we need to have some ECC code to correct or recover the errors for those data. Excuse me. And then we have decoding. Based on the encoding scheme, we can decode the data back to the binary data, like 101010. Okay, so this is the basic process of the DN storage for the read and the write. And also we have the tube concept. I think it's also related to the well concept in the SSD containers based on the previous presentations. So we merge millions of DN strings in one single containers, and we define the tube capacity as the how much data we can store in this container or tube or well. Okay, so this is the basic concept of the DN storage capacity or tube capacity. And there's another two concepts in the DN storage. One is the PCR process, another is the random access one. So the PCR process, I think after the pandemic, people have been familiar with the PCR because of the COVID testing, right? So the basic operations of PCR process is try to duplicate the target DN strings, right? And for the random access, basically we can, based on the PCR process, to amplify the target DN strings, and then we increase the densities of the target DN string, and then we can sequence out of those target DN strings. So this is the basic idea of how do we use the PCR to achieve or implement random access-based DNA storage. So here, for example, if we have the target DN strings, and then we have the primer as an indicator. So we use a primer for the PCR process. For example, for the target DNA string, we pre-know, okay, what kind of the primer pair we have associated with the payload, and then we use the PCR process to amplify the target primer pair. And based on, for each iteration, we can duplicate the number of the DNA strings by 2 times. So for example, some of the PCR process have 10 iterations. That means you amplify the target DNA strings for 1,000 times. Okay. Once the concentrations of the target DNA string reaching to the threshold, and then you can easily use the sequencer to sequence the data out for the target DNA strings. So this is the basic process of the PCR and random access in the DNA storage. And based on this process, okay, then we formulate the DNA storage tube capacity, and which is following these simple equations here. So we said the tube capacity equals to the payload encoding density is based on the encoding scheme, right? So previous simple example, we have 112A, 002A, 012C, and so on and so forth. So basically, we have 2 bits per nucleotide, but based on the bio constraints we have, so it's really hard to achieve the 2 bits per nucleotide. So basically, we have smaller encoding density, 2 bits per base pair. And then we have the payload length, so typical about like 300 base pairs, but we can expand the length to 1,000 based on the biotechnology development. And also we have parallel factor indicate how many DNA strings we can associate with 1 primer pair. So this is the empirical value. It's about 1.5 million DNA strings associated with 1 primer pair. And also the number of usable primer. So this is the indicator or ID or indexing for the random access, right? So the first 3 terms here of variables here is restricted by the current biotechnologies, okay? And the last one, the number of primer, the number of usable primer is kind of, we can use software or data management algorithm to avoid. Okay, so this is kind of the target of this work. So we try to enlarge the number of usable primers in the DNA storage. Okay, probably you have the question of why we want to enlarge the number of usable primers. Okay, so let me introduce that part. So first of all, because of the bio constraints or some requirement in the PCR process, so we do have the primer design rules. So normally the primers has length of like 18 to 25 nucleotides. And to generate the primers, we do want to follow these rules. For example, the GC content, we have the GC content about 45 to 55%. We have melting temperature, 15.5 degree to 16 degree, and also the homopolymer constraints like smaller equal to 3, Hamming distance, and so on and so forth. So this is kind of the primer design rules we have. Okay, so whenever we generate 1 primer, we need to check all those rules, whether it satisfies those rules. Otherwise, it may increase some errors during the PCR process or increase the difficulties of the sequencing PCR process. So here's some bio constraints example. So the GC content, we want to have the range between 45% to 55%. So for this example, we have 6 nucleotides. We have AGG-TTC. So if we just calculate the ratio of the GC content is about 50, is exactly 50%, right? So which is satisfy the requirement. Also, we have some other cases, like if we only have GC nucleotides here, it's 100%, it's increase the difficulty because it's really stable for this kind of GC nucleotides, and it's really hard to like be attached to like helix strings, okay? And on the other hand, if we have all ATT stuff, so it's kind of unstable structure, and then we may generate some errors here. Okay, so this is kind of why we want to have this kind of GC content range. And for the homopolymer concept, so for this case, if we have a TTTT, this is a long homopolymer definition, so we want to avoid such kind of patterns in the DNA strings, because when we detect the signal, if there's a long repeated sequence, it's really hard to say how many of those repeats happened in the DNA strings. Okay, so this is why we want to avoid long homopolymer as well. And for the Hamming distance, if we have 2 like primers, and we just position-wise, we're just counting how many different there. So for this example, the first one is different, second nucleotide is different, and so on and so forth. So basically, for this example, the homing distance is 7. Okay, so we do want to have a large difference between two primers so that they can individually do the PCR sequencing process. Okay. And also we have the primer collisions in the primer library or designs. So possible, so if we assume the length of the primer is 20 nucleotides, and based on the simple calculation here, so we can have all A, C, and so on and so forth, right? So the ideal one, ideally we may have 4 power to 20 number of primers, so which is about 1.1 times 100 times 10 power to 12 number of nucleotides. It's a huge number, right? So this is a huge number. However, if we try to find out what available primers we can use for the PCR or sequencing process, random access basis. Okay, so we may have 28,000 primers because of those kind of primer design rules and also the primer collisions as we introduced in the previous slides, right? So this is kind of the constraints we have. This is significantly reduced the number of the available primer. So it's about like 2.5 times 10 power to negative 6% of the total amount of available primers. And not only that, we also have so-called primer-payload collisions because all those primers need to attach with a payload. And if we have millions of DNA strains in one container, right? So it may have some chemical reactions between the primer or payload. So here are the definitions of the primer-payload collisions. A pair of the long, almost identical subsequence between a primer and any payload stored in the tube, and then it may increase some error rate or increase the difficulties of sequencing. So this is kind of a scenario we want to avoid. And for the similarity, so for the the subsequence, we may check whether this similarity larger than 12 bases, and also we may alone at most 2 mismatch or gap in this amount of like subsequence. Okay. And and after considering the primer payload collision, how many available primers we have? So previously we have 28,000 available primers after the primer design rules and also primer collisions. And now, after considering the primer payload collisions, the total amount of available primer is 8,000. Okay, so it's further decreased, right? So it's kind of 3 times less compared to the previous primer library after considering all those primer design rules. So this is significantly reduced the number of primers. And based on the reduced number of primers, how do we find the tube capacity? So here, this is a simulation we conducted to identify the tube capacity. So first of all, we try to like gradually increase the amount of data stored in the ones, for example, DNA tube or DNA containers. For example, every 10 megabytes encoded into the ATGC sequence. And at the same time, we want to check whether the newly generated payload have primer payload collisions with the existing primer library. If there are any collisions happen, we may want to filter out all those collided primers. Okay, so there's 2 curves. One curve indicates how much data we store in the tube or container. The blue curve here indicates how many available primers we have based on the current amount of data. So the blue curve will gradually decrease because more data stored and more collisions happen between the primer and payload, right? So when these 2 curves reach into a cross point here, this one indicates, we have this amount of data, we can use such amount of primers for random access-based DNA storage, right? So if we further increase the amount of data in the tube, we may not have enough primers for random access purpose, right? So based on our simulation, the tube capacity here is about 211 gigabytes. Of course, There's some like parameters we can tune based on the BLAST simulation. So the BLAST is kind of widely used sequence, the nucleotide oligo checking tools for example, primer collision, primer-payload collisions. Okay. And here we investigate different state-of-art encoding schemes, the influence on the tube capacities. So there are 5 state-of-art encoding schemes: the church, rotational code, and so on and so forth. And the second column here indicates the encoding densities, bits per base pair, and also the capacity without considering collisions, also the practical tube capacity. So based on the investigation here, you can see some of the encoding schemes only have about hundreds megabytes tube capacity. So it's really, really small amount of data can be stored in the random access-based DNS storage based on our simulation. And the rotational code have a really good one, but still about like 210 or 220 gigabytes. So it's far from the expectation of using DNS storage as archive storage, right? So the conclusion here is like there's a huge like capacity reductions, about 70% to 99% reduction due to the primer-payload collisions. And all 5 encoding schemes face such kind of issues. And we investigate different type of data as well, like image, audios, videos, all different data types also face such kind of the problems, right? Okay, so because of that, we propose so-called collision-aware encoding or coding schemes. So the principle or the rationale behind the CEC scheme is we try to trade off some encoding densities to design the payload with special pattern to avoid or reduce the potential collisions between the primer and payload. Okay, so if we go back to look at the primer design rules. Okay, so first of all, the primer don't have any long homopolymer with length larger than 3, and also don't have any consecutive complementary sequence with length larger than 4, and GC contents range about 0.45 to 0.55. So then for the sequence pattern of the payload, we try to avoid the similarity between the payload and primers. So then we may want to design the payload sequence with no long homopolymers, and also any 20 base subsequence of the payload should be fewer or no consecutive complementary sequences. And also any 20 base subsequence of the payload should have more balanced GC content. Here we assume the payload, the primer length is 20 base pair. Okay, so this is kind of the goal we want to achieve. We want to distinguish or make large difference between the primer sequence and the payload sequence. And here is a little bit more details about how the CEC schemes perform. So first of all, we have the binary stream here, and we split the binary stream or group every 3 bits as a one chunk, and then we encode each chunk based on the mapping table here. So for example, we have 001, and then we just look up the mapping table. 011, there's a 4 potential DNA triplet we call candidate. So we will pick up 1 DNA triplet to encode this 011. Of course, there are some rules we will introduce which candidate we want to select for this, for example, the chunk or the block. Okay, and also we will look at the previous 70 bases to check, for example, interdisciplinary and so on and so forth. Okay, so here are the 2 basic key points here. We want to look back at the last base to avoid forming the homopolymer with the last nucleotide. What that means here, if we have some previous last nucleotides here, for example, A here, and then we may not choose ACT because AA will form a homopolymer, right? So we may choose another one, for example, TGA or so on and so forth. Secondly, we look back on the previous 17 bases. We target on less complementary sequence and balanced GC content. Okay. And here's how do we select the DNA triplet from the mapping tables. So initially, each B triplet have 4 DNA triplet candidates, right, based on the mapping table. And we have some priority rules to check. First of all, we want to check whether we have homopolymer formed or not. So this is the highest priority we want to check. Secondly, we will check whether it has less complementary sequences or not. And then we have the strict balanced GC content. So here's one example. So assume we already encode the first 17 bases. And based on the first priority check, so we check whether this is the last nucleotide, it's A here, and 0, 1, 0, based on the mapping table, we have 4 candidates, ATC, ACT, AGT, TGC, and GCA. So based on the first check, this is A here, so we don't want to form the homopolymer. So these 2 candidates will be kicked out, right? Because if we select these 2, we will form the AA something, and then it's formed the homopolymer. And secondly, after this check, we will left 2 candidates here, and there's no homopolymers for these 2 candidates, and then we will check the complementary sequence. So for this example here, the GCA will form less complementary or shorter complementary sequence, and then we will select the GCA to encode this 0, 1, 0. Okay. And for other cases, for example, if still after this the complementary sequence check, we still have 2, for example, more than 2 candidates, we will go through the GC contents check. Okay. And which one give us the more strict balanced GC content, then we will select that one. So this is an encoding table generation. So from the bit triplet to the base triplet. So there's 4 principles we want to follow. First of all, there's no internal homopolymers because for the whole DNA payload, DNA storage payload, we don't want to have the homopolymer, right? So first of all, in the encoding scheme, the candidate itself, we need to avoid the homopolymer. And second one, different starting bases. So this one will help us avoid the homopolymer when we encode the data with the previous 17 bases. Third one is the complementary pairs. So we may want to have 1 and 2 are the complementary to each other, 3 and 4 are complementary to each other. And then the GC balanced candidate, we may have different choices. For example, we may have the first and second one have 1 GC content, and the third and fourth one have 2 GC content. So if we check the overall GC content, we may choose the first one or the second one based on the previous condition. Okay? So this is the basic ideas how do we build the encoding table. And here's the experimental result. So this is about the number of available primers. So there are 3 schemes we evaluate. The rotational code, which is the best encoding scheme for the random access one in the previous table. The CAC is our proposed one, and the exhaustive search is based on our principle. We try to exhaustive search what is the upper bound of the available primers. So if you look at this figure here, basically our schemes can double the number of available primer compared to the best rotational code in the 5 state-of-the-art scheme, right? So for the tube capacity one, we achieve 300 gigabytes, around 300 gigabytes, and the exhaustive one can have 320 something gigabytes, and the rotational code only have 210 or 20 gigabytes. So we kind of increase the tube capacity by 40%. Okay, so here is a little summary of these 3 schemes. So for the rotational code, it has really high encoding density. It's about 1.57 bits per nucleotide, but has really low collision avoidance. So for ours, we balanced between the encoding density and also the, the collision avoidance. So for the exhaustive search one, is avoid a lot of collisions, but it will take a lot of time to search for the potential candidate. Okay. So here is the execution time. So we have encoding time and we have decoding time. So we normalize the execution time based on the rotational code. So for the other state-of-the-art encoding schemes, they have relatively small execution time. Ours encoding time is about 10 times, and maybe for the exhaustive search, the encoding time is 100 times. But for the decoding part, you can see the exhaustive search around like 800 times more than the rotational code. Ours is around like 0.34 because we have the mapping table. We can just have the complexities of 1 to search, to decode the data back, okay? So based on this one, you can see the CEC1 have really good balance between the execution time, encoding density, and also the tube capacity. Okay, and also we investigate the variance of our encoding scheme. So we may encode like 4 bits per DNA triplet. We may encode 3 bits per nucleotide. This is the scheme I introduced. And we may encode 2 bits per DNA triplet. Okay, so based on the investigation here, you can see the number of the usable primer is kind of increased when you increase the number of bits per DNA triplet. But the tube capacity is not always increased. The reason of that is this is kind of trade-off between the collision avoidance and also the encoding densities. When you decrease the number of bits per DNA triplet, the collision avoidance becomes higher and higher, but the encoding density becomes lower and lower. So you need to, based on the tube capacity equations, so the tube capacity is proportional to the encoding density multiplied the number of usable primer, right? So when you have the encoding density decrease, but available primer increase, so they kind of cancel with each other. Okay, this is why for the 4 bits per nucleate, 2 bits per DNA triplet, we have kind of lower tube capacity compared to the 3 bits per DNA triplet, okay? Okay, here are the conclusions of this work. So basically for the, we investigate the issues of DNA storage, the tube capacity, the practical DNA storage capacity is much lower than expectations. And based on the investigation of the observations, we propose a new collision-aware encoding scheme to improve the capacity, and we propose a new mapping table. Also, based on the experimental result, the CEC can improve the number of available primer by 2 times and the tube capacity by around 40%. So here is the kind of the potential improvement. Okay, of course, this is just a start point of in improving the tube capacity for random access-based DNA storage. So we may propose some new encoding schemes to avoid primer-payload collisions, right? And also we can use an error correction code because when we use stronger error correction code, some of the bio constraints become loose and then relaxed. And then you can generate more number of primers, right, for the sequencing of random access-based DNA storage. And maybe we can use longer primers. For example, right now here is kind of 20 base pair. Maybe you can enlarge the length of primer to 25 or even longer, okay? So then you may generate more primers. And higher encoding density. Here we have the encoding density about 1 bit per nucleotide, but the ideal case is about 2 bits per nucleotide. So there's kind of a gap between the ideal case and our proposed one. And also there's more potential there, okay? So here's the acknowledgement about our collaborators and the student, and also the Alliance, NISF, and also SNIA, and so on and so forth, okay? So that's it for my presentation, and please feel free to ask questions. Thank you, yeah. Sorry, I don't have the last slides about take the survey, okay. Thank you, guys, yeah. Yep. Yep. Can you repeat what is the last sentence you mentioned? Yeah. So the question is, when we read the data, we just read the samples of the data, right? Yeah. Yes. So basically, based on the previous presentation, basically we assume, okay, there are a tube store maybe millions of the DNA strands, and then we pick like 1 droplet out and then put into the sequencing machine. Or even before that, we may go through the PCR process for the random access-based DNA storage. Yeah. The sequence is just based on what we read? Yes, yes, yeah. We want to rewrite. So there's a huge amount of copies in the DIN storage. Yeah, it's not just one copy there. Yeah. So you just, for example, you have the one tube contain maybe millions of copies, and then one droplet made just one of those copies. Yeah. So this is kind of basic assumption. Yeah. Any other questions? No? Okay. Then that's it. Thank you, guys. Yeah.